Before starting quantum mechanics, first we have to know why we need to learn quantum mechanics. So for that purpose, we have to read some experiments. We have to learn some experiments like blackbody radiations, quantum effect, photoelectric effect, etc. Because when we learn it, then we will know what was deficiency in classical mechanics that we need a new mechanical system like quantum mechanics. So we are starting with blackbody radiations. For understanding the whole blackbody theory, first we have to be habituated with some terms like emissive power. And emissive power, before starting the blackbody radiation, first we have to learn some terms to understand the theory of blackbody radiation. So our first term is emissive power. When a body emits radiation, then the emitted heat is proportional to area of the body and the time in which the heat is radiated. So we can say that the emitted heat is proportionate to the area of the body into the time of the emitted radiation. So we can write Q is equal to R into AT, where R is our proportional constant which we call emissive power. It depends on the material and wavelength. Now we will learn what is spectral emittance. The power which is emitted from a body per unit area per unit time at a given wavelength through a unit solid angle. We have to remember these terms because it's a definition. We write this spectral emittance as E lambda equal to dq lambda, it is the heat radiated, divided by dA, which is per unit area, dt, which is per unit time, d lambda, which is per unit solid angle, and we have written here lambda, which defines that, which says us that it is constant. Now we will learn absorption coefficient. What is absorption coefficient? It is a ratio of heat absorbed by a body and heat incident on body. For ideal reflector, the heat absorbed by a body is 0. So our A will be 0, and for our ideal absorber, A will for ideal absorber, heat absorbed by body will be equal to heat incident on the body. So it will be equal to 1. For our spectral absorptive power, we represent it by A lambda, which means that the heat absorbed by a body and heat incident by a body, we find this ratio when lambda is constant. Here when we write lambda, it means that for this thing, for this calculation, lambda here is constant. We write same thing like in partial derivatives. Now come to absorption coefficient. The change in energy as the wave passes through a layer is a constant of material for a given wavelength is called its absorption coefficient. It means that a wave passes through a material wall, let it be its thickness d, then it loses some of its power. That loss in power is a constant for particular material for a particular wavelength. We call it absorption coefficient. It is not that much important like absorptive power or emissive power in our upcoming series, but as we are learning this, we should know about absorption coefficient. Now we will start black body. First we will define what is black body. A black body is such a body which absorbs all the radiation falling on it at any temperature at any incident angle. As we have seen that for ideal absorber, A will be equal to 1 as the heat absorbed by body and heat incident on body will be equal. So for our black body is a ideal absorber. So A will be equal to 1. It has zero reflection, it has zero transmittance. Now we have to remember a thing that reflection and emission are not same. Reflection means that to reflect others' wave, and emission means to produce waves on own body. Now we will learn why we call a black body a black body. Black bodies are very poor reflector, so they appear visually black. But to judge it, our eyes are very poor instrument to detect radiation. It can only detect radiation in the range of 0.4 to 0.7 micrometer wavelength. Since the visible part of the spectrum is part of the electromagnetic spectrum, if something is radioactively black, then it has to be visually black also. That means that the radioactively black bodies are visually black, and all visually black bodies need not to be radioactively black. Here are some examples we have written of black body. For our theories, this last example, an isothermal enclosure, will be important. Let's read Stephen's law, Stephen's-Boltzmann's law, and Kirchhoff's law. First, we will watch the statement of Stephen's-Boltzmann's law. The emissive power of a black body is directly proportional to the fourth power of its temperature. Rb proportionate to A into T to the power 4. And we can write it as Rb is equal to sigma into A into T to the power 4, where sigma is our Stephen's constant, which is 5.86 into 10 to the power minus 8 watt per meter to the power minus 2 into Kelvin to the power minus 4. For normal body, Rb will be equal to eta into sigma into A into T to the power 4, and for black body, Rb will be equal to sigma into A into T to the power 4. So when we divided R by Rb, we will get the value of E. We call E emissivity for a given material. For black body, E will be equal to 1. In normal case, E always keeps its value between 0 and 1. Now, the Kirchhoff's law states that the ratio of spectral emission power R lambda T to the spectral absorptivity A lambda T for a particular wavelength lambda is the same for all bodies at the same temperature and is equal to the emissive power of a perfectly black body at that temperature.